Information and Communication Services Limited, New Zealand. Updates on quantum computing. Quantum computing represents a paradigm shift in how we process information. Unlike classical computers that rely on bits, quantum computers harness the principles of quantum mechanics. These principles are superposition and entanglement. Superposition allows qubits to exist in multiple states simultaneously. This unlocks a vast computational space. Entanglement links qubits in a way that their fates are intertwined. This enables complex calculations not possible with classical computers. Quantum computing tackles problems impossible for classical computers. Imagine simulating complex molecules or breaking today's encryption. These are glimpses of quantum computing's potential. It promises to revolutionize fields like medicine and finance. The journey towards practical quantum computers is challenging. Building stable and reliable qubits is a major hurdle. Qubits are sensitive to their environment, leading to errors. Researchers worldwide are working to overcome these challenges. Significant progress has been made, bringing us closer to this new era of computation. In 2019, Google made a groundbreaking announcement. Their quantum computer, Sycamore, performed a specific calculation in 200 seconds. This task would have taken the world's most powerful supercomputer at the time thousands of years. This achievement, dubbed quantum supremacy, marked a turning point. It demonstrated that quantum computers could outperform classical computers, at least for certain tasks. Google's experiment, while limited in scope, ignited excitement and investment in the field. It provided tangible evidence that quantum computing was not just theoretical, but had the potential to surpass classical limits. This milestone spurred further research and development. It pushed the boundaries of what was considered possible with quantum computers. However, it's crucial to understand that quantum supremacy in a specific task doesn't mean quantum computers are ready to replace our laptops. The task Google's computer performed was carefully chosen to demonstrate quantum advantage. It wasn't a practically useful problem in itself. Nevertheless, it signified a crucial step towards building more powerful and versatile quantum computers in the future. Building practical quantum computers requires more than just demonstrating quantum supremacy. It demands the development of fault-tolerant quantum computers. These are machines capable of correcting errors that inevitably arise due to the delicate nature of qubits. This is a significant challenge, as quantum errors are more complex than their classical counterparts. IBM, a pioneer in quantum computing, has made notable strides in quantum error correction. They have developed techniques to detect and correct errors in real time, improving the reliability of quantum computations. Their approach involves using multiple physical qubits to encode a single logical qubit, which is more robust against errors. This redundancy helps protect the information encoded in the logical qubit. IBM's research in error correction is crucial for the long-term viability of quantum computing. As quantum computers scale up in the number of qubits, error correction becomes increasingly essential. Building fault-tolerant quantum computers is a complex engineering challenge, requiring breakthroughs in both hardware and software. Section 4. Quantum computing in the cloud. While large-scale, fault-tolerant quantum computers are still under development, companies like IBM and Microsoft are bringing quantum computing closer to users through cloud-based platforms. These platforms allow researchers and developers to access and experiment with real quantum computers remotely. This accessibility is vital for accelerating innovation and exploring the potential of quantum computing. IBM's Quantum Experience, launched in 2016, was one of the first cloud quantum computing platforms. It provides access to IBM's superconducting transmon qubit-based quantum computers. Users can run algorithms, experiment with different quantum circuits, and explore the principles of quantum computing. Microsoft's Azure Quantum Platform offers a similar service, connecting users to quantum computers from various providers. Cloud quantum computing platforms democratize access to this revolutionary technology. They allow researchers worldwide to contribute to its development and explore its applications. This accessibility fosters collaboration and accelerates the pace of discovery in the field of quantum computing. Section 5. Shaping the future quantum computing's impact. Quantum computers could revolutionize our lives, from unbreakable encryption to personalized content delivery. In healthcare, they promise advancements like accelerated drug discovery. They could also aid in climate change solutions like efficient solar cells. However, quantum computing presents challenges. including job displacement and ethical concerns. Responsible development and collaboration are crucial for harnessing its benefits. Establishing ethical guidelines and addressing societal impacts will be essential.